So now we're going to look at the effect of the magnetic field on a current carrying wire in the magnetic field. Now remember that if we have a magnetic field, for example pointing into the board, and in this magnetic field we have a positively charged particle moving in the upwards direction. So let's say that the charge is positive. What is the direction of the force here? Well, we're using the right hand rule. V is pointing up, index finger, B is into the board, middle finger, F is pointing towards me. So the force acting on this positive charged particle is pointing this way. Now let's think about the current. What did we say about the current? We said that current is basically the motion of positively charged particles in the wire. So let's say that now instead of one single particle, we have a number of particles. So let me draw it here. So this is our magnetic field pointing into the board. In this magnetic field now, I have a wire, and in this wire there are positively charged particles, and all of them are moving upwards. So this is a current flowing in a wire. So what happens then? Well, the same kind of force will be acting on each of the particles, which means that there will be a total force acting on this wire pointing to the left. Now, we can show that the magnitude of this force is given by ILV sine theta, where I is the magnitude of the current, L is the length of the wire, L is the length of the wire, B is the magnitude of the magnetic field, and theta is the angle between the B field and the direction in which the current is flowing. It's the angle between the B field and the direction in which the current is flowing. This expression for the force can be derived from the expression for the force acting on a charged particle moving in the magnetic field. However, the derivation of this is beyond the course. Okay, so we're going to use this as a final result. Now, sometimes we are interested to know not the actual force acting on a wire, but the force per unit length. The force per unit length would then be just F over L. So this is force per unit length. And according to this, it's just equal to I B sine theta. The units of this would therefore be Newton per meter. The units of force are of course just Newton. So now let's look at a few examples. Let's say that I have magnetic field pointing into the board, everywhere into the board, and I have 3 wires. Let's say that the current in this wire is going up. The current in this wire is 0. The current in this wire is going down. Well, according to what we just discussed, there will be a force acting on each of these wires. And the force is found using the right-hand rule again, just as we did it for the magnetic force acting on the charged particle. So here, however, the index finger will show us the direction of the current flow. The middle finger will show us the direction of the magnetic field. And the thumb will show us the direction of force. So let's look at this one. Current I is pointing up, magnetic field is into the board, so F is pointing to the left. So the force acting on the wire here is pointing to the left. In this one, there is no current, so there is no force. So the force here is 0. Here, the direction of current is opposite. Current is pointing down. Magnetic field B is pointing into the board, so F is pointing towards me. So F is pointing this way.